Alright, hello everybody. My name is Lucas Sanchez, and today we are kicking off our semester of Process Dynamics and Controls. This is our first assignment of the semester, in which we revisit a problem we have seen before in our material energy balance class that we took our sophomore year, and we look to apply some new concepts to it. So I'm going to start here on my iPad, and I will break down the problem for you guys. We'll start the screen recording on the iPad, and we'll start talking about it. So in this problem, we are going to have a tank, a cylindrical tank, as best as I can draw it, and into the tank we'll have some flow rate coming in. We'll call it Qn naught to start. Out of the tank, out of some tiny area, a whole of tiny area, we have a flow rate coming out, which is Q out. And we are assuming that at the start of this time frame that the height is of a given value and that the flow rate into the tank is equal to the flow rate coming out of the tank, and therefore we have a steady state tank that is not changing in height at all. So we have a defined height to start, height 0. So we want to explore the impact that would occur on the height of the tank, the liquid level in the tank, when we change Qn by some given factor. So we want to see how the height will go up if we increase Q naught to some other given Qn value. And then we have the Q out still. So in order to do this, we need to understand the flow rate out of our system, Q out, and what that might be equal to. And to do this, we are going to look at Bernoulli's equation. So Bernoulli's equation, we know, is an energy balance. So we are not going to look at the heat loss due to friction or anything like that. We are going to define it in simple terms. So we have two states, and I'll kind of draw this a little better so we can get a better look at what this might look like. So we have state 1 here, which is the initial value, which is the height of our liquid tank, the top of the level, and we have 2, which really actually is at this hole here. So we know that the pressure, Bernoulli's equation is the injection work per unit mass plus the potential energy per unit mass, which is G. In this case, we'll call this Z1. We'll use the variable Z for height, Z1, plus the kinetic energy, which is V squared per unit mass over 2. And we'll call this V1. And that's equal to, at state 2, P2 over rho. The rho, this density is the density of water. So per unit mass, we're going to use water. Plus, again, the potential energy at state 2, plus the kinetic energy at state 2. So in order to find Q out, if we know the area of the hole, or the area of the outlet, we also need the velocity of the outlet. And this V outlet is also known as V2 down here. On this works here is you have meters squared times meters per second, and that will give us the flow rate of meters cubed per second there. So we need to use this Bernoulli equation to find a relationship for the V2 here, to find the V of the velocity of the stream coming out of the outlet. And to do this, we need to make some assumptions about the system. So the first thing we're assuming is that the tank's open to atmosphere. So P1 here, so the tank is open to atmosphere, is equal to atmospherics, as well as P2. P2 is also open atmosphere because of the hole at the bottom. So P2 and P1, both these terms are atmospheric. So if we want to solve we can do P1 minus P2 over rho W. But since they are both they're both the atmospheric pressure, these will cancel out and be 0, so this term cancels out here. And then we have plus GZ1 minus, or G plus GZ2, or Z1 minus Z2 here, which is the difference of the height. And G, since G is the gravitational constant, so we know that 9.81 meters per second squared. Meters squared per second, meters per second squared. And since we know that the gravitational constant is acceleration, it has a direction, and it's acting in the downward direction. So this will be negative G, so we can change this to minus G Z1 minus Z2. And since this is the downward direction, we will use a height convention for the downward direction to cancel out the negative sign. So we can assume that Z1 here is this height, this is Z1, is equal to 0. And Z2 is equal to some height that's not equal to 0. So we'll get negative G times negative Z2, which is a negative height, because we're going saying this is the 0 state and this is a negative state to keep consistency with the direction of the gravity. So this just becomes 0 plus GZ2 now. And then for the velocity term, we know that the velocity times the area is equal to flow rate. And we're assuming that this hole at the bottom, this outlet, is much smaller than the cross-sectional area, which is here, all across here, the cross-sectional area of this tank. And we know that the area of the outlet is much smaller than the cross-sectional area of the tank. So since the area is much smaller at the outlet, the velocity is most likely to have a larger impact on the flow rate coming out of the tank. And so we can assume that the outlet velocity is a lot larger than the inlet velocity. So we'll just assume that the velocity coming into the system of that water is 0. So we'll say plus 0, and that will be equal to V2 squared over 2. So now we have a nice relationship to describe our velocity outlet. So we'll just take 2GZ2 is equal to V2 squared, and V2 it will be equal to the square root of 2GZ2. And since Z2 is basically just the height of this column, we're going to take Z2 out and call this the height. So we'll say V2 equal to square root of 2GH. So now we know the now we know the velocity of the outlet, so we can use that to kind of set up an equation for our system here. So we know that Q in minus Q out will be equal to the change in material, the change in volume of our tank, which is the cross-sectional area times the change in height over change in time. Then we know Q out is equal to minus, which is equal to the area of the outlet, times V2 here, which is 2GH. And that will be all equal to AC DH dt. So in order to investigate the impact of the change in height, because that's really what's going to change the volume in the system, or how we're going to calculate the volume in the system, we need to isolate the dH dt term in order to establish our differential equation. So we'll say dH over dt is equal to Qn minus the area of the outlet times square root of 2g times h to the 1/2 all over the cross-sectional area in the system here. So in order to solve this differential equation that we're going to use to investigate how the height changes over time, and consequently the volume in the tank changes over time, we're going to now we're going to need some initial value conditions. So at time equals 0, we said that the tank was at steady state. So we said there's no change in height. So Q in minus Q out is equal to 0 because it's in steady state. Liquid in equals liquid out. But we need to get this initial height in order to get, we'll just need an initial height to solve this expression because we're solving for h, so, or for the height. So we need an initial guess or initial value for h to solve this differential equation. So at t equals 0, this term was 0 because there's no change in height. dh over dt is equal to 0 because the height's not changing. So we have 0, and you can just basically ignore this AC term because you're just going to multiply by 0, equal to Qn minus A out times the square root of 2 g h to the 1/2. So we'll get Qn is equal to A out times square root of 2g times h to the 1/2, and again Qn divided by the area outlet times the square root of 2g equal h to the 1/2, and h, this will be h naught. We'll call h naught here because we know the initial height, h naught here will be equal to Qn over the area of the outlet times the square root of 2g. And that is equal to that whole expression is squared. So now that we have these initial guesses, we're going to use some different methods to investigate the change in height of the tank. The first thing we're going to use is Excel using Euler's method to approximate the value of this differential equation. So Euler's method, dH, we'll set our differential equation back up, approximates the value of the function using different time steps. So I'll set this up to make it, so dH/dt, we said, is equal to these values up here, so we'll just copy that, paste it back down here, make sure we're not missing any terms, perfect. So dH/dt, so the Euler method will approximate this change in height based on a given defined time step. So it will be dH is equal to Qn minus A out times the square root of 2g times h squared all over AC, and this will be times delta t. I didn't leave much room there, so let me shrink this down for myself. Times delta t. And delta t is something we'll define in our Excel sheet, but this method is not favorable because it's a first order method of approximating the value of the change in height. So it won't be as accurate as the second method we'll investigate, which we'll be using Python. And Python will use a function from the scipy.integrate library known as solve IVP. And there's different methods that we can use in that solve function, but we'll be using the RADL method. So we can discuss those methods further, but I'm going to end this video here and transition to Excel, where we'll take on plotting the change in height over time based on what we've established here. Alright, so now that we have derived the necessary equations that we're going to use to solve for the change of the height of the liquid level in the tank, I'm going to take it over to Excel to apply the Euler method. The Euler method's a way of approximating differential equations using a first order approximation. So I'll start by defining the equations that we started before. So we had change in volume, dH/dt, times the concentration or cross-sectional area of the tank were equal to Qn minus the area out times the square root of 2 times the gravitational constant times the height of the tank. I'm going to put this like this. So this was our change in volume over time. So like I said, so we're going to approximate using the Euler method, and that would basically just take this side of the expression. dH will be equal to the right hand side of the expression, that in parentheses, times dt, and we'll define dt just here in a second. And that will be all divided by the cross-sectional area, because it's on that left-hand expression there. So in order to solve this differential equation, we need some initial values. Like we said, at t0, we need to find h0. In order to find h0, let's define some other parameters first. So the cross-sectional area of our tank will be 1, and that's in meters squared. The area of the outlet will be in 0.2 meters squared. The gravitational constant will be, make sure I'm putting a period after these, 9.81 meters per second squared. 9.81 meters per second squared. What else do we need? We need the initial Qn naught, and that is going to be equal to 0.1 meters cubed per second. Are we missing anything else? Now we can find h naught. So h naught, as we all know, we set that equal to, h naught was equal to, when t equals 0, dht went to 0, so it's at 0, so it's qn. This would be easier for you to find these first. So let's define these with the name, or create a selection. So now they're defined instead of just being floating. And we're going to say, so h naught equals qn naught, because h naught is when the float is still at steady state, divided by a out times the square root of 2 times the gravitational constant, and this is all raised to the second power. Yes, we want something. So h naught is about 0.172 meters. And then let me just check the parameters, make sure we're using those that were defined in this problem. That looks right there, but it seems like the factor of 10 too large. Yeah, goes 2. Area. Alright, we should be good to go then. Area of hole on the outlet. 1. 0.1. Alright. That should be it then. Unless I did find something incorrectly. Oh, I did. You know what? Should be like this. There you go. So it's, there you go. 0.0127 meters. And then, like I said, we're going to approximate using the Euler method. So in order to use the Euler method, we need to define our dt, so what time steps we'll be taking. So dt, we'll define it as 0.02, and that'll be seconds. So now that we have all this defined, we can go ahead and decide how many steps we're going to take. And let's say we're going to take 1,000 steps, or 10,000 steps. So we'll use this fill feature here. Series and columns, and we're going to fill it 10,000. So there's 10,000 steps. If you go down there, 10,000. So the time at the steps will be equal to the steps times the dt. And we didn't define this yet, so make sure I put this in the name manager. Formulas, selection, left column, perfect. So h, we know that at, I need to add a 0, don't I? Let me insert your shift cells down. So we need at time 0, t is equal to times dt. And the h will be equal to, the height of the tank will be equal to h naught because we're at time 0. So dh, we calculate using this expression here. So dh will be equal to q in minus a out times the square root of 2 times g times, and h will be, we'll just use this cell value times h, the height of the tank, and g is not defined there, it's a gravitation constant, perfect. And then we'll multiply this value times dt, and this whole expression will be divided by AC. I want to see a parentheses somewhere. So 1 more in here, 2 more in there. And oh, we haven't defined Qn. So after we interrupt the steady state flow, we have a new Qn value, and that was going to be equal to 1.5 times Qn naught. Equal sign there. And then let's go to the name manager here. Before we get too far along. Section. Alright, now let's define it. Let's see if we can put that in there. Name. It's not like that. What is it? Not defined. Oh, AC. AC. That seems too big. Let's see what we did. Qn minus A out. See, I'm going to take this dt out and put it here times dt. It's still quite large. There you go. Make sure the parentheses are in the right place, because Qn minus, perfect. All right, that looks nice. So that's our first dh value. So our next h value, make sure we fill this down the column because we are our time steps. So our next h value will just be the previous h value plus the height, and we'll work our way down the column here. So we have all of our changes in heights, and we can see how the tank level will change. So let's go ahead and plot this. Here are our time values. Oop, didn't do that. And then let's go right to the top to insert our plot. So insert, we have our scatter plot, and here we can see how the tank level will vary over time. Let's throw a title on it because the plot is nothing without a title. So let's say tank level over time. And as you can see, in the earlier stages, or earlier steps, there's a sharp increase in the tank level, and then eventually the tank levels out to form a steady state. And we might get a better picture if you shrink dt down a little bit, kind of get a better idea of how long it might take to reach steady state. Here it's about 1 point something seconds. But this way of approximating this differential equation is not favorable because it's only a first order approximation. So there's a lot of potential for round-off error in some places. And we want to turn to another way of computationally solving this problem, and that's why we're going to turn to Python for the next steps. And Python, like I said, we're going to do a very similar simulation, but this time we're going to use the solve underscore IVP function from scipy.integrate, and we're going to use that to use the radon method to approximate this DH value as we change. And it will automatically find the optimal value for DT for us. So it'll give us a better picture of how this tank will change over time. So I'm going to end this video here, and we'll transfer over to Python for the next one. Alright, so now we are over here on Python. We're going to do a similar simulation we've done on Excel, but this time we're going to use the radon method to approximate that DH value and look at how the height of the tank will change over time. So we'll start by importing our libraries. So we'll import BSMP, import from scipy.integrate. You will import solve underscore IVP, and then from plotly.subplots, we'll import make underscore subplots. And then we'll connect to the runtime once I select it will run the cell. So give it a quick second while we wait for it. There it goes. Alright, so just a quick little refresher. What we're looking at was that initial steady state equation. So we had a cross-sectional area times change in height over the change in time. That was equal to some Qn naught value, which is the initial flow that kept the tank at steady state, minus the area, cross-sectional area of the outlet, or it's not the cross-sectional area, just the area of the outlet of the tank, times the square root of 2 times g, the gravitational constant, times the height of the tank. Height is all raised to the second, or the half power, because it's the square root of that. So that was our initial equation, and we wanted to approximate the value of dH/dt. So basically all we'll have to do to use solve IVP is we have to create a function dH/dt, and that will be equal to Qn minus the Qout, which we defined as the area of the outlet times the velocity, which is equal to that expression there, all divided by the cross-sectional area of that tank here. So in order to do this, the solve underscore IVP function needs an initial value for the height of our tank. So let's define our parameters and then get the initial height of our tank like we did before, using that expression we defined. So we'll say the cross-sectional area, that was equal to 1 meters squared. Qn naught was equal to 0.1 meters squared, or cubic meters per second, sorry. And just write a hashtag before that. What else do we need to define? The area of the outlet. Was that equal to 0.2 meters squared? And the gravitational constant, g, is equal to 9.81 meters per second squared. What else do we need? ALGH. We should be good to go. So we'll define H naught, and that's going to be equal to, so we know this expression here goes to 0, since there's no change in time initially, but there's no change in height, so we're at a steady state, so we know it'll be equal to Qn naught divided by A out times square root of b square root 2 times g, and then this will all be raised to the second power. And we have a problem here. Must be something with their parentheses or something like that. Maybe another set will help. Moving that out of A out, defined times NP. Maybe that's the problem. A out times NP. 2 times G. That would be the full expression, but let's see what happens when you plug this in. Oops. Alright, now I try to read the second half. Oh! We're using the wrong sign. There you go. I was using the Excel format, so it needs to be double star. So let's see what h naught is equal to. H naught, that's similar to our Excel value, around 0.0127. So we can go forward with the rest of this. So solve IVP. What it needs, we'll need to feed it the function we're looking to solve. So the ordinary differential equation that we'll plug in is the dH/dt equation. We'll have to define a time span, so however long we want to look at the tank level, and we'll provide that initial guess with this y0 here. And then the method, we're going to use the rad-on method here to approximate the value of dH. So the function that we want to create will be labeled something like dH/dt. Oh, I did it wrong. Define dH/dt. We want to put the time variable first in this bracket, in these parentheses, and then we look at the change in the height. So that's h. So we're going to look at how we're going to plug in the different h values. So we want to look at what happens when we increase q in to some value. So we're looking at increasing q in naught by a factor of 1.5. So obviously we know that's going to run to steady state because you'll have more material coming into the system than material is leaving, and then you'll have an increase in tank height. And then we have this equation here. We'll just copy and paste it because it's pretty much what we'll be solving for. I just want to return. Return q in naught. But instead of q naught, we'll use q in here. And that should be good. Alright, and then we'll see solve our IVP. Or actually, let's define Tn equal to, we'll do 100 seconds right now. So we will do solve underscore IVP. dH/dt will be the function we're solving for. Our time span will be from 0 to t end. Our initial guess, it's expecting a list or an array or something that is more than one element, because it's usually looking to solve a system of ordinary different equations, but in this case we only have one equation to solve for, so we need to input that in a list or an array or a tuple, whatever you want to do. So h naught's going in, and then the method will be equal to the rad-on method to approximate this value. So perfect, we have the solver was successful, and now we wanted to kind of unpack this a little bit more, so we're going to get this dense output. We'll set that equal to true. So we can look at, we'll call this out. And we can look at the different outputs. So out dot t. Oh, I didn't run this yet. So here are the different time steps that it's taking. So like in the previous Excel simulation, we used a defined delta t. This finds an optimal time range or optimal time step to approximate these values of dh. So here are the time steps here, and here's y, our output, or our output of the different heights over time. And one that we notice here is two-dimensional array, and we're not going to be able to plot that. So we want to pull. I'm going to say y, or we'll say y plot will be equal to out.sol, and we'll need that's all right. We need to find a time interval first. So the out.t, they're kind of randomly spaced, and if you want a kind of a better picture, we'll probably want linearly spaced or some order spacing for our time intervals to get a good plot. So we'll define our time interval. T int will be equal to np.arange. We'll do from 0 to 100. We'll do steps of 0.5 for our time range. So we'll take a look at it. So there we go. Oh, it goes too far. 100.5. There you go. So from 0 to 100. And then our y values, so the y plot, will be equal to the output dot solve, and then we'll go t int and that's still two-dimensional, so we want to say, we show the first element. If we able to define it like that, perfect. And that's one-dimensional there. So now we can go ahead and make the plots, or the plots, sorry, not plots plural. So we'll say fig equals make underscore subplots, and then we'll say fig dot update underscore scatter, no, fig dot add underscore scatter. X will be equal to t int, y will be equal to y plot, and then we need a name for our y value, so we'll say, just we'll call it height in meters. Let's see what it looks like right now. Sure. What's wrong with that? Fig that together. So fig dot add. What's wrong with that? Oh, so fig dot add. There we go. The problem is we didn't have these opening and closing parentheses at the end of it. Okay, and then we'll add some different things. So let's add a name title to my tank. Whoops. Oh wait, that's not what we wanted to do. this, we go to fig dot update electrical layout. Title will be equal to height of tank over time. We'll call the size equal to, or height equal to 500, the width equal to 1,000. Yeah, x-axis title. Yeah, we'll just take the recommendations there. This now. Oh yeah, can't use capital. And there we have what our change in height looks like. So it'll shoot up in the early time state steps, and then it reaches a new steady state at a value of about 0.286 from there out. If we increase the time t-end to maybe here's so we will do it 20.5. We'll get a better idea of what the height is shooting. So it's actually even do like 3.5 and see what it looks like. So here's a better idea of how quickly it's changing after we increase that flow rate into the system. So shortly after this, we're going to take a look at a new step to this problem, in which we'll have 3 tanks in series, and we'll look at trying to find a value of a control constant, and then applying that to this 3 tanks situation. So I'll shortly switch over to that. Until then, this is what we have for the first part of this problem. Alright, so we first just discussed a situation in which we had 1 tank and we increased the flow rate by a given factor, and we investigated how that tank and the height will change, or the height of the tank will change. Now we're going to look at a situation where we have 3 tanks that are identical to the first part, and they're all in series. So I'll start by drawing this out. So we have 1 tank. This is the tank that was initially involved in our first simulation. And we have the Q in naught, initial flow rate, and we have the flow rate out, which we have Q1 out, and we discovered that was equal to the area of the outlet times the square root of 2 times the gravitational constant times the height of the tank. Directly flowing from tank 1 will flow into tank 2. So Q1 out of tank 1 becomes Q2 in, basically. And same thing, we have Q1 out coming in, and then Q2 out will flow into tank 3, and Q2 out will be equal to the area of the outlet times square root of 2GH2. So there's 2. And then for the third tank, Q2 out is Q3 in, and then that becomes Q3 out becomes Q3 out is equal to the area of the outlet times the square root of 2GH3. So, like we had a balance for the first tank, we have, or not balance, we have a differential equation for the first tank that describes the change in height with respect to time. We'll have one of those expressions for all 3 of the tanks. So for tank 1, we have dH1 dt times the cross-section area will be equal to Q in and Q in minus A out. We'll just call that Q1 out because we just defined that up top. Q1 out. dH2 dt times AC will be equal to Q1 out because that becomes Q in, and then minus Q2 out, the flow rate out of the system, out of the tank 2. And then dH3 similarly will be equal to Q2 out minus Q3 out. So we're assuming that these tanks have been in series for a while. They've had a given flow rate, and eventually they're going to achieve a steady state. So all of them will have the same height in the tank, because Q in naught minus Q1 out, since these are both the same at steady state, the flow rate will be the same, then the flow rate into 2 will be the same as the flow rate into 1, and then the flow rate out of 2 will be the same as the flow rate in. So they'll all be in steady state. It's the same for tank 3. So H naught in tank 1 will be H naught for all of these tanks. And we saw for H naught previously, we know that H naught is equal to Q in naught divided by area of the outlet times square root of 2g. This is all to the second power. So we knew that already. Now we're going to look at something called proportional control. And proportional control is where we set a gain constant and add it to a certain variable that we're trying to control based on another parameter. So in this situation, we're going to proportionally control tank 3. Tank 3 will be proportionally controlled based, or no, sorry, tank 3 won't be proportionally controlled. Oh, it will be. But what we're controlling is the height of tank 3, and we'll have a given height set point. And we want to control tank 3. The only thing we really can control is the flow rate coming into the system. So Q in naught will be increased based on the difference in the set point. So to give a numerical expression to kind of illustrate that relationship, so Q in will now be equal to Q in naught plus the gain constant, Kc, times HSP minus H3. So the larger that this difference between the height set point and the height in tank 3 becomes, the more you're adding to the flow rate, the more you're adding or subtracting to the flow rate coming into the system to adjust that level in tank 3. And we'll head over to Python to kind of illustrate its impact on the system and how each of the tank levels will change with this given controls, this given proportional control system. Alright, so we're over in the same collab notebook that we started with for the first tank. We have our plot that we had made it before. We're going to use some of the same conditions that we used before, so we're going to take these from the top, bring them down to the bottom here. Oh. Okay, runtime again. I guess I didn't really have to do that. I can just move this down a bit. We'll define them down here again. So all those initial conditions will stay the same, but now we have a new function that will help to define. So since this DHT was looking at one tank, it won't suffice for our situation, but we'll start again with a new tank. So we'll define a new function. We'll call it DHT3. DHT3. And we want it to, we'll put it in the time. And now we're going to return a vector, because we'll have 3 height outputs that we're looking for, so we'll have to unpack a vector here. So we'll say h1, h2, h3 will be equal to spec. And now we have the fun part of defining all the heights, the flow rates out of the system. So in this situation, we were able to get away with saying, we had only one flow rate looking into the system. So now we'll have to change that up a little bit to get the DHT value. So we'll have to say Q1 out, Q2 out, Q3 out will be equal to, so Q1 out will be equal to what is Q2? Think about this for a second. Q2 out. This goes to 0. Oh, sorry. Q2 out equal to A out times NP dot square root 2 times G times H1. I was totally blanking there. And put this in parentheses. And then Q2, or sorry, that was Q1 out. Q2 out is equal to the same thing, but instead of H1, we're going to use H2, the height of the tank 2. 2 times G times H2. And then our third height will be equal to, yes, the area of the outlet times the square root of 2 times G times the third height. So now we have our three flow rates, and we can look at returning the values that we're looking for. So we can return, it'll be Qn not, or just be Qn, sorry. And we'll have to define Qn. Actually, Qn minus Q1 out, and this will all be divided by a C, the cross-sectional area. And then Qn minus, that's not it. We'll need Q1 out, become the flow rate into Q, or tank 2, minus Q2 out. And this will be divided by AC. And then finally, yes, Q2 out divided minus Q3 out will be the dHdt for the third tank. So we haven't defined Qn here. So let's just start with a random value. Qn will equal to Qn not times 1.5. So we'll see what happens when we increase by a factor of 1.5. So we'll shift enter. So let's see if this solves. Solve underscore IVP. Our function is dHdt3. Our time span, what do we use for the last one? We had 0, 0 to, do we have a Tn defined somewhere? No. Another T-span, 0 to 50, okay. We'll use, just go to 100. 0 to 100. Our initial guesses for all three of them will just be H naught. H naught, H naught, H naught. We're still going to use the rad-on method. And we want dense output to be true again. Perfect, so we solved. And here you might notice that we have multiple sets for y. So we have an array with however many, 3 rows now. Instead of just 1 row, we have 3 rows, so 3 sets of answers, so 3 sets of outputs to plot. So we wanted to find this as something to get a look in to plot this. So we'll say out is equal to solve IVP. So out.t, like before, we kind of have some random time steps that it generated, it optimized it using the rad-on method. So you want to again define, we'll use T-span, we'll use up here. But we'll go to 100 seconds. 0.5 T-span. And let me bring these both down a little bit. Let's move down. Control N J. Oh, that's not it. We'll just move this down as best as we can. I think I deleted this cell. Alright, well, T-span, now we turn it to a text cell next thing, which will be down here. So we'll say out dot sol, and we just need T-span. We no longer need the first item in the dot sol or out dot. We'll just say out. We don't need the first item in this array because we have three rows. So it will pull. So we'll say we need all 3 of the rows recently. So we need H1, H2. So H1 plot, H2 H2 plot, H3 plot would be equal to out.sort. Let's see, take a look at what it looks like. Alright, so we have some values at the appropriate time intervals for each of the plots here. So now we can go ahead and plot this. So fig equals make underscore subplots. I'm going to generate that. And then fig dot add scatter. Perfect. X equals t-span h1 plot. Tank 1. We'll do the same for the others as well. X equals t-span. That will fill in for me. So there we can get a look at what that looks like. We'll change the t-span a little bit because that's a bit too long. So here's how all the heights will change. So as you can see, the height of tank 1 will shoot up first. As that height increases, the flow rate out of the tank will increase, then increasing the flow into tank 2. This will increase this height, and finally, as tank 2 increases, the flow rate out comes. The flow rate out of tank 2 will increase the flow rate into tank 3, and that will increase there. So now we're going to introduce the idea of the proportionality control, or proportional control. So Qin will no longer be just a given factor. So Qin will be equal to plus Kc, which we haven't defined, times the height set point minus the height of H3. So we haven't defined either of those terms yet. And we'll move down here to do so. So we're going to do something. I'm going to use a for loop to iterate through different values of Kc in order to get an idea of what we want for our given, find the optimal value of Kc that doesn't increase or decrease the oscillations and the plots. So we'll define HSP here as 1.2 times H naught. Let's see what we have for HSP. So there's HSP, so it's about 0.152. 0.0152. And now we're going to go and iterate through this Kc. So let's say for I in range, we'll go to 30 for K. For I in range 30, so Kc, we go to Kc plus 1. Let's define Kc up here as Kc is equal to 0. So each time it goes to the loop, it will add 1 for the Kc. Now we want to use, let's define this function here. So now the function's defined. So now we can go ahead, yes, perfect. We can say solve underscore IVP. We can just take this whole expression and paste it back in. This time it's not solving for that same function that we defined to make these subplots, because we have introduced this new Qin value into our expression. So we'll see how that changes the behavior. So out equals K solve IVP. This will be the same. So H1 plot, H2 plot, H3 plot will still equal all the given values for the heights at the different times. And then we want to plot them the same as we just did. So we want to make a scatter plot for all the different Kc values. But this time you want to add a title so we kind of distinguish the different. You can distinguish between the different Kc values. We want to know what we're looking at. I don't care too much about the height. Right now I'm just going to look at the title, and that title will be equal to let's say liquid height in tank over time with value of Kc equal to plus true Kc. So let's go ahead and run this and see what happens. Say fig That looks a bit too sharp. Something's wrong here. Alright, so we just troubleshooted. Right now, our plots look something like this, and it's because of the time span that we defined. So it's a pretty long time span, 100 seconds or whatever we're plotting to now. So we want to kind of tighten it up, but you can see, even still, the plots are oscillating just not as cleanly as you'd like to see, just because of how large the time span is. So we'll go ahead and change the time span here. So instead of a range, we'll say t-span equals that within space 0 to 10, 200 plots per second. So there's an idea of what that would look like. I don't even know what the KC value is equal to right now. But here's what we want to do. Iterate through this for loop, and that will generate the plots with the different KC values and kind of show us how the change in the KC value will impact the oscillation. So here at the beginning we have a set point. What was our set point again? 0.052. So a KC value of 1, it doesn't even get us to the set point, so it's not enough. But before that even happens, the tank level 1 shoots up, and then 2 follows, and then 3. So here again shoots up. We only get to about 0.03136. And now you can see the oscillations are starting to grow a little bit more back and forth between the levels and all of them. You can see a sharp spike in height 1, followed by the increase of flow rate out of tank 1 into tank 2, so that will increase tank 2 and its change in height. And then you can see the oscillations continue to grow as we increase this KC value. So oscillations are growing, they're still growing. You can see them kind of peter out over here now. Oscillations keep growing. We're still growing here. We're still going, we're still going, we're still going. Oscillations still growing. And then it gets to a point somewhere in between 20 and 30. Here you can see the oscillations are still growing quite a bit, but growing in magnitude, but not in frequency. They're about the same frequency in all of them. So we'll say at about 22. I guess here's this. But yeah, 20 to 30 is where the value we're targeting, and we're going to learn a new method in class shortly, I believe, to kind of pick out an optimal KC value. Instead of just looking at the plots, probably numerically determine this value of KC. But if we try to go more than 30, something that's worth looking at, just say, we'll go make a formula for it. We'll just say KC equals 31. So we're unable to solve the 3 differential equations just because KC is too large there. So it is unable to solve that function, so we can't even plot that. So somewhere between 20 and 30, my guess would be 22 to 23 would be a range that we're looking at. But we're going to look at a way to kind of numerically determine that number. And we could even decrease the step size here, kc equals, but that would take a long time, so if you can say I is equal to 20, and we can say like kc is equal to kc plus 0.5 instead now. What would that do? We'll say I plus kc plus I plus 0.5. So now we can get a little bit more better idea. And so we're just plotting and looking at these plots. So there's a better way to do this. I'm not sure how to do it at this point. Yeah, here are the oscillations. You can still see them growing and growing and growing. And they get to a certain point where it's about similar for all of them. But that will be it for this homework. And I'm looking forward to finding a better way to find that optimal value of kc in the future.